Hello, my friend, and welcome in this new episode. Today, we will be talking about ray marching. This is a simple example that I've been constructing in the Nerveland project, and let's just show you immediately the result that we can get currently on this topic. So here is a simple scene that I have constructed using a ray marching mechanism. In case you don't really know what this means, ray marching is a bit like ray tracing if you want. So you don't, what you see here are a sphere and a rounded box, but you don't really have those objects here in the scene. And you are rather, well, computing the display for every single pixel with a formula which is taking into consideration the sphere shape and the box shape and their position and so on. So yeah, you're processing every pixel using this underlying formula, if you want, to describe your world. And so the idea I have is to try to, well, provide some initial indication on how you can achieve this this kind of result in the WebGPU. And we will start from the very beginning up to the final result that we get here. So let's get started on that. First thing I did was to create a new example file here. And this one is very simple actually, because all we really need to do here is to basically render a quad align, a screen align quad. And everything is going to be done directly in the shader itself. So there is not really much to do with the setup of the object that you need to draw. In my case here, what I'm going to use is a draw call with 6 vertices, because by default the setup that I have here for my full scene rendering system is to draw triangles, simple triangles, and you could achieve this result in fact drawing only a single triangle, which is slightly more efficient, I guess, in cases where your shader is very expansive, and it's actually maybe going to be the case with ray marching here, because ray marching can become pretty expansive in the end, because you do a lot of computation directly in the shader itself. So probably something to consider here, drawing only a single triangle. And the idea is, when you draw a single triangle, you draw a triangle which is bigger than your actual viewport, and you have to ensure that this triangle is covering completely the viewport, and you have part of this triangle that are going outside of the viewport, and they're not going to be rendered at all. And this is more efficient than using 2 triangles, because the main issue with 2 triangles is normally if you use 2 of them, you're going to draw one triangle covering half of the viewport, and the other triangle covering the other half. And the problem here is you have a diagonal here, and to render this diagonal, the fragment shader is going to well, since it's going to compute the pixels, usually using 4x4 pixels, I believe, because when you have the threads executing on the GPU, you have I don't know, I think you call that warps of 16 threads, and these are usually drawn using 4x4 pixels, I think. Anyway, there's something like that is the underlying reason for this. So you're doing computation for pixels that are going to be discarded in the end on this diagonal. So that's a waste a small waste, but a waste anyway. So you may want to consider, as I said, using a single triangle here. Apart from that, the only important thing is to perform remarching, you need access to your camera position in the world. I mean, you could go ahead and try to hardcode that directly in the shader, but well, if you want to be able to navigate around like we're doing here, here we have the camera position updated for each frame. What else? You are then going to use also, in fact, the camera transformation matrix. So you have the projection matrix and the camera view matrix. Because the idea is you will start with your quad that you want to draw. And from that, you are going to assume that the vertices that you have for your quads are giving you a quad line, a screen aligned quad. And so you're going to use the position of those vertices to get back from the clipping space into the camera space. So you would use projection transformation and invert your transformation. So you get the vector then which is in the camera space. And then using the view matrix, you would get from the camera, you would have a point in the camera space, and you would use a direction from the camera position. And this direction vector, you will transform that to get it into the world space. So using the camera view matrix. Those two operations, so we can just maybe start looking into the shader itself there. So those two operations, you're going to do them in the vertex shader. So this part here is how I get UV coordinates for my vertices. So remember, I'm only receiving an ID here, which is from 0 to 5, since we're drawing 6 vertices in my case, and the UV here are going to cover this 0, 1 area in the X and Y coordinates. Then you're going to convert that into clip coordinates for your position. So you take UV, you remove 0.5, and you multiply that by 2. So you get values between -1 and 1, both on X and Y. You just assume that this position is on your far plane. So in the clipping space, you have this box if you want, so -1, +1 in both directions. And for WebGPU, it's from 0 to 1 on the Z-axis. So the far plane means 1 normally. So then this clip position, you're going to transform it back into the camera space. So that's why here we get the projection matrix from the camera uniform buffer. This is a standard uniform buffer, which is going to be provided by my camera class here. And for every frame, you're going to get the projection. Yeah, projection is here. So retrieve the projection matrix from the actual camera object and send that to the GPU. Same thing for the view matrix. And yeah, what I've added lately is this camera world position. So to get this, you just get the view matrix and the transformation of it. The view matrix here is yeah, I mean, it's the I always mix. It should rather be called the inverse view, but I'm calling it the view here. Yeah, I mean, there's a mismatch between what I'm calling view and inverse view on the GPU side and CPU side. But yeah, never mind. You just need to get this sorted properly on your side, I guess. Anyway, what was I saying before that? Yeah, you take your clip position, clipping space position. You unproject that actually, and you get your unprojected vector. Then you consider this as simply a direction vector in your camera space. In your camera space, actually, the camera position is 0, 0, 0. So if you want to just consider the vector which goes from this unprojected position to your camera, well, that's unprojected minus camera position, which is 0, 0, 0. So that's just the vector of your target point, if you want. So the unprojected X, Y, and Z position. So you take this as a vector and you invert this vector using the invert model view matrix, which is a transposition of the view matrix. I guess I could just as well use the inverse matrix here because I have that available, right? I think it would work also. I mean, maybe this is something we can try. Inverse view matrix, where am I providing that? So in the LCD camera UBO, we have inverse view matrix here. So I'm thinking if I was doing something like UBO point, use this matrix here, that should still work. Okay, seems to be okay. Alright, so in the case of the view matrix, taking the transposition of the matrix is giving you the inverse. What is the assumption here? I'm not quite sure to remember exactly. I mean, this works for rotations and I'm not sure it works for the translation part. Never mind, I don't need to think about it for now. Anyway, let's get this back to default implementation here. So once you've done that, what you will end up with is a vector which is basically telling you for the current vertex that you are considering what is the direction from the camera position to that vertex, but this direction defined in the world space, so the world frame. And so this is one element that you need. The other part that you need is the actual position of the camera, so the starting point for all your rays. So you're going to have rays going from this vertex and another vertex and so on, and all of them are going to start from the camera position. But you need this camera position also in the world frame. You probably can retrieve that directly from the matrix that you have, the view matrix. Actually, this is what I'm doing in the code here. Starting the view matrix, get the translation part. You could do that directly here. It's just that I basically never remember what is really the ordering that I have for the element of my matrices here, so I didn't want to think about it. Was a bit lazy, so I've just added this additional uniform vector, which is a camera world position, so retrieve directly from the C++ side here. And that's actually the most complicated part in the setup for your ray marching project. What I've been using then is this article here from Michael Walczyk, something like that. And this is very nice, and the explanations are simple enough for me. So I could use that as a starting point. And the idea is we need to build a few of those distance fields. And for instance, for a sphere, it's a simple function like this one. So assign a distance field. And what was it? Yeah, next part was you need this, a setup of a ray marching process, because when you start from your camera position and you have a direction, the thing first you need to understand is you're doing the computation here in the vertex shader, but you're going to send that to the fragment shader, which means that even if you only have 4 vertices, you're going to have those ray and origin vectors interpolated for every single fragment that you're going to compute afterwards. Except that for the origin, all the vertices have the same value, so the origin, the camera position in the world, is not going to change. Only the ray is going to be progressively interpolated between 2 separated rays. And what you need to do then in your fragment shader, you get those inputs, you just try to normalize the ray first, and then you start doing your ray marching process, starting from the origin point and using this ray, which is specific to your current fragment. So this ray march function, this is basically what we have here. You start from a position and you're going to progressively move forward. So the current position here is your origin plus a number of steps using this ray. But what you need to do, yeah, it's more like this implementation, because for every step you're computing what is the distance that you get in the complete world, actually. So it's a bit like what you have here. You start from this camera position here. Well, though, just during the first cycle. So let's say the camera would be here, and you compute the distance, and you see that the distance is given by this point. So you have this circle where you have no object. So starting from this point, you can then move to the next one, which is here. And here you compute the distance again, and you get this location. So there's no object in this full circle. So you can keep moving in this direction up to this point. Then you get this one, so you can move here. Then you get this one, so you can move here. And normally this, well, if there is an intersection in the world, the radius of the circle is going to get smaller and smaller. So this whole process is performed here in this ray marching function. So the initial version which was provided was this one. What's happening here is you have the number of steps. You start from your ray origin, camera position at start, and you start traveling in your ray direction. Total distance would be 0 at first, and you're going to increment that progressively by computing different distance. So let's get back to the simple version. So here what we were doing at first is not all of this. And also I have been tweaking a few of those settings. So let's get back to the original value. I think the number of steps by default is 32, specified here, yes. And the minimum hit distance is 0.001. Let's skip the other one. So you're going to try to perform those 32 steps. And the distance here, we're using a new function here, but at first we were just using the distance to a sphere. So the distance to a sphere is this function that I'm using here, the st sphere. So let's use that. You give it the position of your current pixel, your current world position of the point you're considering, and you have the center of the sphere and the radius of the sphere, which should not be changing normally. So here you would do that, and you would use your current position, which is what I'm providing already, and at the center of the sphere, let's just say we are at the origin of the world, and the radius of the sphere, let's just put that to 1. So you're doing your computation, and in case basically the distance that you're computing here is very small, it means you're getting very close to a surface that you want to display. So what we were doing at first was just to display this as a fixed color, let's say just full red. So that's exactly what we have implemented here. Otherwise, if you notice that the distance that you have traveled so far is getting way too large, it means probably you have objects somewhere around you, but the ray you're considering is shooting towards emptiness. So at some point you will pass all those objects that you have in the scene, and when you start computing the radius of the circle where you have nothing around you, this radius is going to get bigger and bigger. And if you keep adding that to go even further from your actual scene content, your radius will keep growing, and at some point you will be way too far away. So that's what we have here with this maximum trace distance set to 1000 units currently. If this happens, you don't have anything to display, so you just get the background color. And the background color is what we have here, 0.2 for red, green, and blue. If this happens also, we stop here, we just break, which could in theory be way before we have performed those 32 iterations. So that's a good thing to do. And otherwise, we keep adding to the total distance that we have traveled since the camera position itself. And using this implementation, so basically we're just using this ray march function and the SD sphere here to get the distance with respect to a sphere. That's all we do in the fragment shader. Using that, you should just get, maybe if I save the file first, of course, you should just get this display. And now I can still move the camera around, which is going to change the origin point and of course update all those ray directions accordingly. But yeah, when you do that, you don't get any kind of visuals apart from a fixed red color, because this is what we're computing and returning here, just a red color. So the next step from that, let's see. Well, here you have a few details on how you compute those rays. I've tried to explain that already. I guess here it's a fixed camera position, but we went a bit further than this. And this was the original implementation. Okay, then the shading part, which is important also. You need to figure out, once you have found a point where you actually have an object in your scene, you need to figure out what is the normal of the surface of this object in the scene. And to do that, it's explained here, but well, you can build a simple function. But yeah, the first thing is, which is a good step to take, I guess, you definitely want to have a function which is going to be able to give you the distance for any point in your world. So that would be this map the world function here, taking just the position of your current the current point that you're considering in the world. So let's restore this part, which was already implemented here with the map the world function. If we just replace that, I can get rid of this. So in the map the world function now, we're going to do the same computation here with a sphere, and for now let's just say this is the only thing we need to return. So in the end, this is not really changing anything compared to the previous implementation. We just have a dedicated function now returning this distance field value for any point in the world, considering all the objects we want to consider in this world. Because the idea then is you're going to modify this function progressively, because here you can add other objects, merge them together, compute intersection, unions, or whatever. And we'll get an example of this a bit afterwards. So that's the function that was suggested here. And then using that, you can actually compute the normals of any pixel, any location in your world. And this is described in other articles, in fact, but I didn't really need to think at all about it. I just took this implementation and, well, transformed that into WebGPU. And this is what we have here, the calculate normal. And after that, you can move to the next step, which is going to be to maybe just display the normal that you have computed for this point in case you have an intersection with an object. So you use your current position, which is the location where you are currently at, and you can compute the normal. And let's just display that. But the normal could also be, well, in XYZ coordinate, you could have negative values, so you really want to take half of it and add 0.5. Shader is saved, so let's see. And that's a result of the display of the normals on the sphere, which is working just as expected in the end. After that, once you have normal, then you can start considering more advanced display. So let's just not display that anymore, but you can consider, for instance, that you have a light source somewhere in the world again, world coordinates for everything here. What you're going to compute then is the direction of to the light. For that, you take your current position in the world and the light position itself, and you can compute a diffuse intensity value using this dot product here with the normal that you have computed for your surface. And finally, we're going to just return this red color, but modulated by the diffuse intensity. Okay, and if we save that and run again, now we have this red color with the diffuse shading in place. Cool, isn't it? All right. I think this was actually the next step mentioned in this article. Yeah, light computation. So we have the similar content here, and you get this result. Next thing they were suggesting is you can start modulating your content next, and you can modify the shapes of everything in the world. So for this part, actually, you can just try very different stuff. But let's just give you an overview of that. So if we were just to return the sphere plus a displacement. That's the kind of result that we get. And what we can see actually here is I have a small defect, if you want. Well, first defect we have is this. If I move, you can see that the consistency of the shape is basically changing. And the other defect are those, I'm not sure we can see that on the recording, but maybe, yeah. Those areas where you don't have any content rendered, it feels like the ray is passing through the shape and it's not considering that there is an intersection at all. And depending on how the camera is positioned, those effects are more or less visible. It's usually when the ray is getting close to a tangent direction to the surface that you're considering. And actually, I have found later what this problem was, and it's all about, I think, the number of steps that you're considering, because the other option that could happen here is you go through this loop trying to find a point, a distance that is smaller than this value that you have specified, and you use all the steps available and you still don't have such a point. Which, if you think about it, makes sense if you are getting tangent to a surface, because you have a surface maybe at this level and you have a ray coming this way, so maybe you are at a position just above the surface here, but when you compute the circle you have a small radius, you're still not touching the surface, so you keep moving on the ray direction, adding the small radius, so it's moving you just a little bit forward but not so much, and then you compute another circle and you get a radius for your sphere, which is basically the same as the previous ray. So you keep moving again just a little bit forward and you will get a lot of points like that, not moving so much because you're getting close to a surface and you have a lot of points, but you at the end you have all of those points and you're still not touching the surface itself. So in theory, if you perfectly tangent to your surface, well, that makes sense. You're not going to display it because you're never going to touch it. But then even if you have a small angle between this ray and the surface, the number of steps that you take may be important to consider. So one way I found could deal with most of those display issues was to increase the number of steps, which is a pretty large value now if you think about it. But I would expect that this would get rid of the display artifacts. Well, it's getting rid of the second issue that I mentioned, the fact that we had holes in the surface, but we still have this pumping effect on the. I'm not quite sure what this is. Maybe this is related to the second thing I've changed here, which is the minimum hit distance. No, we still have this effect. Okay, this one I'm not quite sure what it is. So maybe something still to be investigated later. But yes, after that, I think this was the conclusion of this part. Next thing I was considering, and this is actually very nice to keep track of. If you are interested in ray marching, you definitely want to, well, follow this guy, or I don't know, read what is writing, check what is available on the shader toy. So let's go on this page, or maybe, yeah, I already have that. So Inigo Keyless. I guess that's how you say it. Sorry if it's not the proper pronunciation. On this page you will find a lot of articles on how to deal with signed distance fields, and one which is particularly interesting for me here is this listing here, where you get the function that you should use for different kind of shapes, and you have different links everywhere, and you could have a look at those because it's very interesting. That's a simple one, but maybe if you go on the page for Inigo, yeah, this one is providing a few very advanced examples on what you can achieve with ray marching. So I definitely suggest you go and have a look at this, because thinking like, okay, when you're displaying that there's actually no mesh, no polygon or anything, it's pretty amazing. This one also, for instance, terrain rendering with ray marching can give you a very nice result. So yeah, and here you have a list of different simple primitives that you could draw. Have a look at that, and really you should read whatever you can read concerning this guy, because he is really, well, just a genius actually. But anyway, I've started with this page and I just said, okay, maybe I can try to use another shape in my world, and I went for this one, the round box. And also, if you want to display two shapes in your world, everything is going to be changed now in this map the world function. And you can just display a simple box like this. That is going to give you the dimension of the box, and this is going to give you the radius of the roundings. And you still compare that to your current position in the world. And on top of that, what you can use is actually the concept of the translation for all those objects. So you can apply that to any object, of course. And yeah, for the positioning here, what you would do is this kind of operation. If you have a point in the world and you want to display a given SDF primitive with some transformation, then what you need to do is to invert this transformation and apply it to your current position before doing the computation for the actual SDF primitive function. And that means that for simple translation, for instance, if you want to display your box translated by 3 units on the x-axis, you need to invert this translation of 3 units on the position that you're given as input. So that's going to be exactly what we have here. To invert the position, the translation is to apply a minus, and you use this as your new current position if you want. And that would give you the image of the box, but translated of 3 units on the x-axis of the world frame. The next thing you need to consider is how are you going to display 2 shapes at the same time. And to do that, the easiest thing to do is to consider that you're going to display a single shape, which is the union of those 2 shapes. Even if they are separated, it doesn't really matter. You can just compute the union of them. And the union is another kind of operation which is described here. And that's it. To compute the union of 2 objects, all you need to get is a minimal distance computed for those 2 objects. And this is what I've tried to provide here. Which means that if we display the scene now, what we expect to see is the sphere still in the center of the world and a box on the right side moved by 3 units. And in fact, this is exactly what I was displaying at the start of the recording. And yep, that's it, guys. One last thing I think I could demonstrate is how I discovered the issue I was discussing about a few moments ago, because I was still at that point using those 32 steps. And I'm not sure it's meaningful to change the minimum hit distance, so maybe using just this value is okay. But yeah, with only 32 steps in this scene, what you get is something a bit weird when you start moving here and you well, you can already see that at the top of the box here. When you start going down, you will see that part of the box disappear, because again we have too many steps to move forward and get close to the surface, and so we're basically giving up. Now this display is incorrect, and you can also see that if you, well, here also you have something incorrect. You have some space between those two objects. It should not be there. And the surface here, yeah, for the cube is going to, the box is going to start disappearing. So not much left of the cube in this case here. So that's why, as I said, the number of steps can be important to define the results. I guess, yeah, you could get similar effect on this side. So not correct. And yeah, from there, I think the idea for me would be to try more of those shapes and maybe start considering a bit more of those other articles I've seen, for instance, concerning the display of terrain. That could be very interesting. So I'm going to read more about that and see if I can produce some look at that. Man, wow, I really need to try something like that. And when I get something like this ready, I'll make another recording for you. And meanwhile, yeah, if you're interested in remarching, as I said, look at this page. And if you have any question, of course, let me know in the comment. And see you next time. Bye bye.